Hello, good morning to you all. This is Engineer Michael Chola, your usual culprit, sharing industry practices, experience, lesson learned with your colleagues in the same field. Definitely, I'm a PMP practitioner, registered engineer with ERB, Engineers Registration Board of Uganda, and member of Uganda Institutions of Professional Engineers, and a mentor and a coach in and outside workplaces. Many of you, some of you, we interact, and my mentorship more or less is geared towards getting registration with the ERB and UIPE, and also in general practice. I'm also a member of PIAC, International Road Association, majorly in the technical committee in bridges. I think between 2024 and 2024, that's it for 3 years. It will expire in 2027. Today I'm sharing knowledge on steel composite bridges. Composite in the sense that it will have two materials differently, and the common material in practice today is basically concrete and steel. So you very well know concrete is good in compression and steel is good in tension, and the two can give you a very good robust structure. And as you can see here, basically I picked this from the internet, defining this red stuff. This is the girder, this is the steel, these are the steel girders, and this is the deck concrete with the side safety barrier or parapets or crash barrier. That's that with these steel railings. These are guard rails, and down here you have a deck system which is in concrete, and then you have a girder which has interconnections of steel beams with diaphragms and the rest which shall sit down. So basically that is in a nutshell what a steel composite deck bridge is all about. The support system remain your usual concrete. Pier support system, you can see pier column, sometimes with a pier wall, and these are the abutments, or if it is continuous would still be pier, but this is now, when you look at that bearing sits and the piles, then this is the abutment, this is the pier, and continue this side. So basically that is in brief of a cover page of a composite deck girder in a nutshell. That's as simple as that. You are done. So if we proceed to the brief, I try to pick examples of what we do in the industry, and the first thing is the steel composite bridge overview. This is just a typical double span 20 meter, total of 40 meter span bridge. This in a way is it is simply supported with an expansion joint here. So this is your normal abutment here, abutment left and abutment right. You have pier support in here, and then you have your approach railing safety to guide for transition from the road to the bridge, and then you have the guard rails, and then out here. This is a sectional elevation of double span steel composite bridge. So this is steel composite, can be steel and timber, can be steel and concrete, but I think the most dominant now it's steel and concrete. Timber bridges are getting diminishing with time. I think it has its own challenges. So concrete and steel seem to be dominant, and they have taken the day. Yeah, so that is why you can, when we talk of steel composite, by default we are meaning steel concrete. A bit of concept: steel composite bridges combine steel girders or beams. We either call them steel beams or girders, If you read deeper, you will know the difference. But that's synonymous kind of with a reinforced concrete deck. This synergy leverages the high tensile strength of steel and the compressive strength of concrete, resulting in a robust and resilient structure. I've already mentioned above that because steel is very good in tension and concrete is good in compression, when you combine, normally with the response to loading, you find there's a way the whole structure is connected, and because of the two unique features and properties, the combination give a very good response to applied loads. So that's why they are saying here it results in robust and resilient structure. So down here you see this is a typical this was a typical section. We normally try to come up with typical sections so that depending on the road class and the location and choices and the volume of traffic, we already have some of these. So for preliminary design and other things, you can quickly use the rule of thumb and other formula for you to derive quickly and get to have a bit of a brief estimate for concept design and budget planning. So with this typical section, leave alone the dimension, but look at this is the concrete deck, and then this is your surfacing, wearing surface, vary between 550 to 100 millimeters. In practice, if you read literature, I think for bridges, to take care of fatigue and axle loads and so many things, and also for local effect response, the minimum thickness is 220. Some literature talk of 225, but the most dominant is 250 for spans, I think, for spacing about 2.5, from 2 to 2.5. But of course, when you do design, you should be able to check with design to make sure whatever thickness of slab you use passes both ultimate and durability. So it is scientifically derived, though, because of this time which has passed in practice, people now have it known, it's already stuck in their head that normally this is by rule of thumb. You know that let me start with 250 and then you play around and see. So basically you do refining, revising your design, and you get what works, but the minimum should be at least 220. I always see 200, I always see 150, but because if you subject this to fatigue cycle, vibration and other things, you'll definitely start getting potholes appearing and disintegration of concrete and even failure, cracks and the rest of it. So we have to be a bit careful here. So this is a typical section. We have overhang, we have this spacing. Normally this Y is a half of S, so that you don't get so many difficulty in your design, but in case it is not, then still you have to design for it. We have drain pipe. You have to drain this deck here. So you know very well that steel is weak if exposed to corrosion, and therefore this surface water which you collect from the deck slab is always contaminated, and so it is important to discharge below the girders, the steel beams. If you leave it halfway, because of windy rain and the rest of it, normally it will be splashing onto the steel, and with this frequent wetting and drying will definitely aid initiation of corrosion and depreciation in the capacity of this member, losing its section capacity and affecting the global response of the girder, and a bridge can easily collapse with time. So this is the bridge key component. You have the raised walkways. This is the services areas where you can put your duct. Sometimes you can leave it open and you have covers. And then services, always you can clip it also under the overhang. This throat is basically for draining the deck this area. At this point, you're supposed to have a guardrail, but I think it was removed when trying just for purposes of fitting here. So the history is very simple. The concept of steel composite gained prominence in the mid-20th century due to innovations in construction techniques and materials. Engineers focus on optimizing steel and concrete usage together to create economic and durable bridges. Definitely, the issue was more of durability and economy. But now, with the challenges of retrofitting of some of these bridges we are witnessing today in the 21st century, I think the International Road Association, PIAC in particular, and the Technical Committee of Bridges are now coming up with they are coming up with ways of trying to introduce redundant members and also having conservative design in the sense that it will aid or it will ease future retrofitting because you can retrofit with ease if you have some redundant members that will tend to stand in for load path when you are trying to work on some weak members. But today, if you try to retrofit a structural member, because it was economically designed, definitely it has no any other load path to aid that exercise, so it becomes disastrous at the end of it all. So that is why now the whole thing is we need to consider redundant members in all our structural configurations and design and loading analysis and design to take care of that. Though economy still play a bigger role, some value engineering need to be done, but at least it is now well known that an economical design may prove to be difficult to go past the design life we always mention or are proud of. So that is something needed. And then also climate change adaptability structure that will take care of this unprecedented change in the climate. For example, with us here in the Kasese region, that's a district, you have seen the kind of flooding that happens annually. For water from floods moving with very big boulders of at least almost 3 meters and above, and therefore if you have bridges that are on with headroom of within 3 to 4 meters, definitely the structures do get damaged. So that would call for a revision of configuration of bridge spans, headrooms, to adapt to this kind of changes in the climate change. So economy now is still there, but it has to be now proportional to the kind of climate change we have. The advantages of steel concrete is that it has enhanced strength and stability. Steel composite bridges manage heavy loads and challenging conditions effectively. Definitely, it has to be conceptualized. You have to design for it, not just a matter of putting anything and you expose it even to fire and you get into problem. So it has to be well planned for. The strength and the stability definitely comes from how you configure your structure in terms of the stability, how you design the supporting system and the rest of it. But it is very good, it has enhanced strength because you have already seen that steel is very good in tension and concrete also good in compression, so the two combination can take high loading. Cost effectiveness is also part of the factors making the advantage of steel composite. Using steel reduces the amount of concrete required, definitely. Like if you are talking of a 1 meter deep beam girder, that one includes the deck slab. So if you have a deck of 250 and then you have a 0.6 meter concrete with also 0.6 by 0.75, that's too much concrete. Now if I bring in a 0.9 deep girder with a flange of 0.3 and a thickness of 0.3, so you will find that you have reduced. It is lighter, it is strong, and that means even foundation the footprint becomes smaller. It fits very well into this carbon footprint requirement that the world is crying for now. So it has a bit of benefit here. So using steel reduces the amount of concrete required, leading to cost savings and many more. Ease of construction. Prefabricated steel component can be swiftly assembled on site, reduces. So you remember we talk about propped construction and unpropped construction. Even when you are doing your modeling, you have a flowing river, flooded all the time. Is always you have water all year round. So all you need is of design your girders, probably take care of, make sure the loading includes the formwork, wet concrete, construction loading. You take all the loading requirement during construction and then the one in service. So once it is taken care of, that steel girder will be designed for it. And remember, during construction, the steel girder takes the weight of everything on it, be it wet concrete, reinforcement, construction materials, human being on top, equipment which is used. All that weight is taken solely by the steel girder before it has gained composite action. So you design that. So once it's done, you launch the girder, even if it's during rainy season and during floods and water is moving down. For you just launch this thing up, and then from there you using crane, and then you go up, you assemble your formwork while water is flowing and without any problem. All you need is to provide safety nets and the rest of it to avoid any falling object into water. And then of course that's guided by the environmental people in terms of managing environment when you're doing construction. So the benefit of use of steel member is that it is it's possible that you can do unpropped construction, and you are able to do very nice, clean, without any fear, do your construction. But of course the spans matter. You don't need, again, exceptionally long span. So that will again call in for some other way of doing. For short to medium span, you can use this overhead crane to lift and put up, and then you connect all those girders, cross frame diaphragm we are going to sit down, and you're able to do so. It is very easy to construct. All you need is formwork and the reinforcement and concrete. While the girders are already fabricated from the factory, all the connections, the bolting holes and everything will be done, and then you just come and put the thing up and you're done. Applications of steel composite, definitely they are utilized in the highway bridges, road bridges, even river bridge. I think for us in Uganda we have more of river bridges than road bridges. We have just started seeing road bridges with the Kampala flyover. I think we are going to see more. The one we have done completed is a post tension. It's a hollow section girder, concrete post tension, but we are going to see more in lot 2 around Kitgum House and other places. We are going to have a lot of steel box composite bridge flyover. That is where we are going to have a lot, and even VVIP along the Nakosero up to Kampala and bypass was designed, and we had a lot of steel composite, but is yet to be constructed. So the road bridges are still few, but river bridges, we have almost over 60 bridges already constructed since 2015. We have steel composite and the river. They range from 15 meter span to about 30. Some are continuous. So, and then also urban overpasses, this is what I'm meaning. I think we are going to witness them in the next 1 year or two. They're good, they're adaptable, they are strong, and also they have a cost benefit. Now, key components of the steel composite bridge or bridges. Why composite? Composite action comes in when you have the concrete put on top of the girder, steel girder. I've told you during construction you are going to the girder will be fabricated from the factory, put in place with the SIA connectors. The SIA connectors these SIA connectors are very, very, very important element in your steel composite. If it is not done well, then the term composite will not be will not be effective. It will not work. So it has its own design philosophy. The detailing requirements, construction requirements, these are done in the factory. There we have two types. We have the shear studs, which looks like reinforcement bars, but if you look at the heads, they have a different kind of section. All these are determined properly and then designed for and fabricated for. You cannot just cut any reinforcement bar and you put it to work in place of this. No, it will not work well. You will not get that benefit to the extent that will be durable as per the design. Then we have the channel. The channels are yet there's a lot of research being done on the shear connector by channels. Of course, it's also very good. It has its own formula. It has a design philosophy. You have to do so. These are the two key ones. I also see, if you look at BS 5400 part 5, you are going to see other different types. I think hooks and some spiral stuff are all there, different configuration. But this is the two dominant shear connectors. Their functions are to connect steel girders to the concrete deck, promoting composite action. That means that even this channel, you don't cut any channel anyhow. It has to be well. There the dimension requirements, height requirements, width requirements, spacing requirements are all given. So you just need to spend some time, look at the different literature, and then you should be able to guide tomorrow when you find someone doing. I've seen some people trying to weld these normal mile bars that it will work. You can argue your way out, but with time, within 2, 3, 4, 5 years, you will see your bridge not working. You get it? So it is important that when they are fabricating the structural steel in the factory, fabrication of shear studs must be done there. Welding, because the welding is done under controlled condition using this X-ray and the rest of it, and even testing of these. You have to test them whether they are working well or not, whether the welds are adequate or not. You have to check all that. So these are the types are basically here given. They are typically welded stud connectors, which efficiently distribute shear forces along girders, and also channels or hooks. These are some of the types that you encounter. As an engineer, it has to be designed for. You design check. These connectors are subject to fatigue. So in the minimum you checked when you're doing design of steel composite, the fatigue design they will always talk about is going to be more affecting the studs. Why? Because the studs are at the interface of concrete and the steel girders, and every time they are subjected to loads. There is that deformation effect, up down movement. So definitely that is the rhythm that trigger issues to do with crack and other things. So it is always very important. And as you are going to see, when we reach the design of steel composite, you will find that Midas take care of that very well. And when you do your design, you'll find it, whatever spacing on the dimension you have given, it will definitely come. You see here it is 19 millimeter diameter, 100 millimeter high shear stud. You also have 20 millimeter diameters. You also have 22, I think, maximum. It is not anything. You can't use 32 diameters. You have to check. It has to be confirmed. So the standards are there. You just pick from the manual, some codes of practice, and then you use for your design, and it should work very well. Another thing is some of these steel girders come in length of standard length of 6 meters, 10 meters, 12, and 18. Now, if the spans of the bridges you're building, or of a bridge you're building, is about 20 meters, definitely you have to put 12 and 8. So you have a joint. That joint is what we call a splice, and a splice joint or a connection. So we need a connection there, splice connector, which is comprising of balls and both flange and the web. So you see, this is the web. It must have the web plate. with these bolts, which you can see the bolt holes and the spacing. All these have requirement. The H distance, the N distance, the intermediate spacing are all guided by the manual and other literature. You have to be very, very careful that you abide by that. When someone is reviewing or quality assuring your design, that is the area someone pay attention, whether you comply with the standards. These are industry standards that people will look at, and when they say the design doesn't conform, don't jump to conclusion. Just get your design back and have a look at here. So here you have the web, then you have the flange, the plate of the, so because this is the joint, you have to connect this member A with this member B. So the top flange will have to be given. There are quite a number. Midas does not design connections, but there are other softwares that do design connections. We have robot structures, we have Idea Statica, and many more. Even manually, people, you design, professors have given all those approaches, literature. You design that. It's very easy to design, but you need to make sure you get the right load and at the right locations. And most of these splice connections, you don't just locate them anywhere. You have to put them in areas where you avoid subjecting balls to tension, at least shear. Shear is easy. These balls can be designed quickly for shear with minimal stresses generated by bending moment. So they should be kept away from high stress zone, preferably where you have point of intraflexure or where you have zero moment. Is very important so that the design become easier. So please take note of that. It's the same thing you do for your reinforcement in a beam. Where the laps are done, you try to avoid high stress area, and then you do your lapping where you have compression effect, you put the lap. Where there is tension, you avoid lapping in that area. So this is what we have here. So this splice connection joint steel girder segments extending their length, and then must be designed for both for ultimate and serviceability limit state. It has its own design philosophy that you follow. They have the high strength friction grip balls. You can use the normal tension balls. They will tell you so many things. So it is very important. Even balls have to be designed. Balls also have its own philosophy. So it is very important. We shall get time if we try, but this is an overview, just an overview, and I'm only just pointing out that as an engineer, make sure each and every structural element is always designed for. This shear studs or shear connector must be designed for. This girder must be checked and designed for ultimate limit state and serviceability. And then the balls and the plates, both the flange balls, the flange plates, bottom and top, and then the web, all have to be designed for. There are formulae, there are approaches, steps to be followed. Very, very important. So it's not just a matter of just saying this is it, that is it. Even when I come back here, the shear connectors, no, the shear studs also have to be designed. You get it. So now that is about our splice connection, where you have the span exceeding 12 meters, 30 meters, you have to connect, and that is very important. We also do have, I think, two types of the girders. You have roll section, which normally work well up to about 20 meters span, and then you have plates where you connect plates and you do welding. That's more or less factory controlled. Plates go beyond even 100 meters. I think up to around 130 meters. So plate girders are even deeper, because most of these roll sections, I think the deepest is 1016 millimeters. That's 1.016 meters deep, and it is very difficult to do stiffeners, intermediate stiffeners, because it's already done from the factory. It has all the fillet, everything done, and so controlling the deflection and other thing become a bit difficult when you are doing roll section. But for plate girders, you can actually look at precamber and it is done direct from the factory. By the time your girders come on site, you just do your bolting with minimum weld, and you achieve your camber, dead load camber, everything. So when you do your concrete, everything, you find your girder well done. So this is very important item. You don't do this well, the bridge will definitely get down. So it is very, very important that this section is under well. The splice connection is actually your girder. If it is not done very well, always we get disaster. Then we know these girders are always for stability purposes. Before it is concrete is put in place, these girders are unstable against the torsional buckling. So we use either diaphragm or cross frames, angles or channels. So if you look here to the, I think here, the cross frame offer lateral stability to girders, preventing buckling and ensuring the bridge deck remains level. And the configuration usually installed in a cross pattern to brace girders effectively. If we are using angles, like to the right here, then it is in a truss kind of configuration. They are all, it has to be designed for. So as I stated earlier, all the structural elements or all the elements in the bridge must be always designed for. You can see this drain pipe is hanging on a hub. It's supposed to extend all the way at least 100 millimeter below the girder. I've told you the reason why. Because of the contaminated surface water here, we tend to avoid exposing these steel girders to the contaminants to avoid early initiation of corrosion. Then here to the left we have, these are diaphragms. So you can either design your cross stability member as diaphragms or as frames, or which are comprising of channels or angles. So this is the configuration you have. Diaphragm and frame, the transverse structural element connecting girders. Normally, most practitioners do say if these cross frames are only necessary at the construction stage. Why? I think the girders are always at that stage, they are a bit unstable. Wet concrete is not yet in the composite action, but after 28 days, when the deck slab has hardened, has gained the strength, then you find the shear connectors working now effectively, and then resulting into what they call unit action between concrete and steel. So that is now where we derive our name composite action. Now at that stage, the concrete deck system is now bracing the girders laterally, and there should be no problem. So, but normally we do leave these frames and the diaphragms in place just to give more stiffness and also control deflection in a way. If you do better and proper modeling, and you model using frames in place, or you remove it, you are going to see a difference in the deflection of the girders. Well, deflection of girders tend to reduce when you have these cross frames in place, and they tend to go more than required when you don't have these cross frames in place, and that need to be checked. So when you're doing your design, always try to cross check, and don't move quick to remove them. They are necessary in a way, very, very important for bracing. You know, we also need to design for wind, lateral effect. Even earthquake tremors sometimes to some extent can affect, especially for continuous bridges. They are affected by lateral effect. Even during floods, it is important. So it is very important that these bracing systems they even have their guidance in the manual and code of practice and other literature. So it's important that any of you doing this kind of steel composite bridge should be mindful of the type, the configuration, and the detailing. Detailing also is very important. Ensure that the detailing does not affect the structural integrity of the main girders. The main girders here our interests. So you do your detailing and connection in a manner that doesn't affect the performance or functionality of your steel guard. Very important. So these cross frames do distribute transverse loads and enhance stability. The materials, it can be from steel or concrete depending on the design needs. Definitely we can use concrete members to connect steel, but I've seen in some of the major bridge structures they can use steel to brace concrete. But in these small bridges we do basically steel as our cross frames and diaphragms. So these are the key elements of steel composite. We have the shear studs or shear connectors and the splice. Splice is basically a connection, is a medium of linking two short members to comply with the bridge span. But the component of steel composite is basically shear connectors, the deck slab, and the girders, and then the cross frames. Those are the four. I've also included here bearings, just interest area. Bearings are independent, and bearings are designed by the manufacturer. I think today we have Mageba does bearing design, and I think other manufacturers also do. Fresinet, no, I don't think Fresinet does. It is Mageba, which I've seen. Yeah. So if you look at bearings, it allows for control movement caused by thermal expansion, loads, and other forces. In simple terms, bearing is a link between the superstructure system and the substructure system. So that link, it bears the weight of the deck system and transfers this weight onto the substructure system. It is subject, so it also has its own design philosophy that once you are having a design, make sure you also have a separate design of the bearing. Normally what happens is we just require reactions due to dead load and the reactions due to live load, movement, deformations, because those are the information required by the manufacturer. Once you share the information with your reaction with the manufacturer, then they will now come up with specific bearing dimensions that will cater for your load requirements and other data you have supplied. So basically it allows for control movement, so it also take care of some movement due to thermal or even tractive forces. You know, even traffic loads generate movement, so even earthquake generates movement. So as a designer, you look at the total movement. There's movement due to this movement due to temperature, due to loads and other forces, and then you get to know, and then the manufacturer will definitely come up with bearing, because there are different types of bearing. You have the pot bearing, you have the rubber bearings, you have elastomeric bearing, but the most dominant bearing here with us in Uganda is basically elastomeric, because our bridges are small to medium span. For major bridges, I think they have specialized. I've seen the existing steel bridges we have, like the Katunguru, the Pakwach bridge, do have steel bearings. So depending on the weight, span, and exposure, you can come up with the type of bearings, and then the sizes are determined based on the loads, basically, for a proper response. Bearings are prone to chemical, and therefore you need to protect them very well. So your bearing seats has to be properly drained, whereby when water gets into the top of the abutment seats, it should be quickly drained off the bridge. So the bridge abutment should always be dry, kept dry, even the deck system, so that you just only follow on few areas. So from this picture, if you look at this drawing here, this figure here, you find it is flat, but it's not supposed to be flat. You must have some kind of a groove here. When water gets through down here, it should be able to flow towards the wing walls. So this is your your abutment. This is the sole plate of this steel girder. This is the flange. You always have to have a sole plate under which now you put your bearings. Then normally bearings are placed on grouted cement, properly designed, strong enough to take care of the reactions, and so that has to be. So this detail is not up to date. This is not good practice of placing bearing directly on the bridge seat. So it has to be, have a pedestal kind of. So with the pedestal, you are raising it away off the seats, which is always subject to accumulation of silt and dirt, and that is a source where chemicals can get generated from and then affect, because this whatever accumulates down here comes from the surface of the deck, which are already contaminated. So this is your elastomeric bearing. This is the flange of the main girder. This is the flange, no, this is the web and the flange and the sole plate. Then between the sole plate and this bridge seat here is your bearing. This white one is the bearing, which is here. So this detail comes from the manufacturer. So please take note of that. Very, very important. The function is allow for control movement caused by thermal expansion. Load bearing types include elastomeric bearing for flexibility and port bearings for larger loads. Significance: critical for maintaining structural integrity over time under varying conditions. But proper maintenance and timely inspections are key factors in observing the longevity of some of these structures. Very, very important. Don't underlook that. So the future trends, basically continued advancements in engineering and material science promise even more innovative designs and sustainable practices in the realm of steel composite bridges. Now we have high performance materials, stronger, more durable steel and concrete already in the market, which is trying to even improve in terms of span, the robustness of the structure and the rest of it. Post-tensioning thin wall box girders are already being followed. Strong steel box girders using post-tensioning. So I think the advancement is trying to come up with, is going to create more of dynamism in the industry and a lot of innovations. Concrete filled steel tubes, you can see, we always talk about composite. We know encased eye girders and the rest, but now you can see they are talking about concrete filled steel tube, combined strength of steel tubes and concrete for better load bearing. Definitely this is not so new. It's new because it's a tube, but at least we are aware. Personally, there's a building we designed opposite Serena here in Uganda, whereby we encase the eye girder. This not high girder, but the UC column encased with concrete, because it was is supporting a structure, a floor at the third level from ground floor, bypassing first level, second level. That means about 6 meter height, and it was encased. It's performing very well. So that is so now this one is the other way around. Now you have a tube, then you fill concrete. Definitely you can see what it is. I know it works very well, but of course now you need to protect the steel from corrosion, and once the steel start getting corroded, definitely the composite action will start getting affected. So it is very important. Sustainable construction using recycled materials and fiber reinforced polymer for a smaller carbon footprint. So the future trends is promising, and basically, but of course now it is require a bit of reading and doing a lot of following up, because otherwise we shall be left behind. Advanced monitoring systems, sensors and data for real-time bridge condition assessment. Recently VSL took us through how they do the inspection of cable-stayed bridges. I was amazed. Robotic inspection, drones and other things. I think sometime last year also we were in Seoul, South Korea, and we saw how the industry has started embracing use of drones for high altitude inspection and hard to reach area inspection. So you can see where we are going, and the drones can actually even get a 3D scan, and you can also generate a 3D of impression of the bridge you are inspecting. That is how the world is advancing with the technology. Modular construction is happening, prefabrication for faster, more efficient builds, reducing waste. I know in bridges now, like we have this material from France, we have Mabbe Johnson in UK. These guys have quite very elaborate prefabricated modular bridges that tend to speed up the construction works within days. And it is what we have been trying for Baileys. We do it. What delays is only the foundations. We did about 6-7 in the last 10 years, and our delay would be on the civil works. As it is done, that the superstructure is in a day or two, and we are done. So that is very important. Now, that is briefly something which I picked quickly, just a small talk about steel composite. Just for knowledge sharing. No, I'm not a lecturer. I'm not a teacher. For a teacher or a lecturer will know that this is how we should move. But for me, as a practitioner, I jump here, I jump there. I just want you to feel something, and then when you are reading, doing your profession, your philosophical reading, you are able to know, oh, this guy mentioned this one, where is it found, how do I follow it? So basically that's what I'm doing, zigzagging in a way, but of course if need be we can still go in the order required. So now let me dive into modeling using Midas. So modeling, analysis, there's modeling, loading, analysis, and loading, analysis, and design using Midas Civil. So in the modeling, you utilize the steel composite wizard. So we are going to just have a brief look. We already been talking about most of the things. So we are making use of the Midas Civil, and in brief we have been talking about from the time we began talking about Midas, the procedure remained the same. You have to have you have to define materials, you must define section properties, but what I hinted on was, do you know what you are modeling? The most important thing, do you even know, can you draw what you're going to design? As an engineer, if you are supposed to model a bridge, you must understand the whole thing so that you are able, because modeling is an art. Modeling is more like detailing, coordinate system based, extrusion, offsetting, and other things. So if you don't know what you're going to work on, you can't see what you're supposed to model, then it's going to be a difficult task for you. And that is all about Midas. You have to know what you're going to model, and the rest is then materials, section property now come from, you just have to understand the section. If it is a pier column or a pier wall, how are the sections going to be defined? If it is a steel composite, you just need to have a look at. We shall quickly have a look at it and see. So you have to define your materials, you have to do section properties, you have to create additional structure element if required. You have to understand the overall bridge structure to ensure accurate modeling. Even the load path, you must understand that. So if I go quickly here, and then I take you to properties. If I take you to properties, you can see the different materials here. These are the different materials you have to create. You have to create these materials. So this is your first having sketch, because even by the time you go to do materials, you already sketched through the whole project. You have it somewhere. All the sketches, the coordinate system, you have it. So by the time you go to the software now, you are now going just to relay the information so that you are able to model, load it, analyze it, and design. So by the time you come to do all this, you already know. Even the choice for the, now in real world, by the time a structural engineer sits to do the design, we expect hydrologists to have done his part. We expect geotechnical to have been undertaken. You understand the chemical properties of soil. In contact, you also understand water quality, because the exposure condition need to be known to the designer. So it's not an isolated cases where you just sit alone and do the work. You have data from the different experts because of the role play, and then even the geometric design, the profile need to be known. So the highway will have done its part. By the time you are going to model, you know the headroom, you know the final level of the road, which is matching with your top of the asphalt concrete on the bridge. So then you come and you start your issues of modeling. Now you do your materials. You do material that was steel. You can also do for concrete specified. I think for concrete you have quite a number. You see here the different concrete grades. This is an Euro code. So this is a cylinder strength 20 and compressive strength of 25. Cylinder strength of that, a compressive strength of that. So this is where you come and define. Now for this steel composite, you use this one, structural reinforced concrete. It's very important. That is, you need to make sure it is there, and I have it there. So when you click on that, you're going to see that you have the two. You have steel and concrete. So you make sure you specify both properties here, the strength or the grade. That is very important. Then when you come to section, you have the pier column. You also need to know, now you know, you have a column of 1.5. And then sometimes if you are starting, you can design. If it is failing, you improve. Either you need bigger reinforcement, or you need smaller diameter reinforcement but bigger section. Now you see which material is cheaper in the market. That's how you can do your optimization. So you have to define the pier, even pile system, pile caps. Pile cap, this is the pile cap, that is the pier column, and that is the collar beam, and this is the piling system. You define. So this composite action is what I want to show. This is what you have to define it here, and they are different. They are here, so you can do so many. But this is how you define it. You need to know the road class. You need to know the road width from the designer. That's why I'm saying the geometry has to be ready. So you need to know if it is a 14-meter road width, that will be your end to end or edge to edge of your girder of the deck. Then you deduct your walkways. If you're going to have walkways, then you are left. So the most important thing is the carriageway has to go uninterrupted through the bridge. So if the carriageway is 3.5, and then 1.5, that's already 10 meters. That 10 meter which has shoulders and the carriageway will go across, so that when you are driving, you cannot notice you are on the bridge. You don't need to reduce it to be smaller. It has to go straight. Then if you have now your walkways, the walkways start from where the 10 meters end, the 3.5, and the 1.5. So where the 1.5 ends is where now your raised cap starts from. So then you are able now to know the width. You can now determine how many girders you need, and then you know the spacing of the girders and the overhang. So if I can show you here the overhang, this is the overhang we are talking about. So basically you need to be mindful of that. You get it. So this is your girder spacing. This is your girder spacing. I think this is 2.45. And anyway, if you want to know, I could quickly even check what I used. If I have a -5 and I go to 3, that means it's 2 meters. Then this will be 1. So the main girders are 2. So 1, 2, 3, 4, 5. That's already 10 meters. If it is a 13-meter width, that means the overhang here is 1.5, 1.5. So basically, so that is, but definitely in most cases, people have done design. If you look at most of the bridges from Britain, UK, you'll find that they always say 4 girders have been assessed and observed to be more economical. But here I've done 6. That means I would expect of small amount, but you see the problem now, you have bearings. These bearings are many. So if a guy does only 4, the bearings become fewer, but the steel could slightly go higher in terms of weight per linear meter. So all this will call for an value engineering and optimization. So it is very important that you do that. Yes, money. Yeah. So so here you have, there are 6, but the members this section should slightly be shorter, not deep, should be shallow. Yeah, so that is what you need in your section and material definition. The composite section is already given. Normally, if you don't do it, it becomes a problem when you are now trying to model, because we are going to use the wizard. So once you have defined all this, you have defined materials, you have defined sections, what follows now? The good thing with the wizard, even this boundary condition will come automatically. So what you need to do is to know to model it. This loading is where you're going to apply. Some loading will definitely be part of the thing, and then the life load has to come in, the traffic lanes and the vehicle, you see. So if you are done with the material definition and you are done with the section definition, then now you come to the structure, and then when you come to the structure, you go to this is now where you find the steel composite girder bridge wizard. So here there are like 1, 2, 3, 4 components that you need to fill. You have the layout. So in the layout, you have the girder type, which is the composite. You already defined. If it was box or U-tap, they are all here. So there are 3 types here. You have the eye girder, you have the steel box, you have the tap. But we have chosen steel eye girder. So you have, so here what I'm going to do, let me open what I already done, and I show you. So here it is a 2-span, 30 meters. The composite, the width is 13 meters. It is all frame. I can make all to be plate, or deck as plate, girder as frame, or deck and web as plate. So these are your choices, but definitely you need to read about steel composite. It's not a matter of jumping to the software. You also need to understand very, very well the philosophy behind it. Yeah, so down here, these are the bearing type. If it is with structure, you substructure. This is now what it is. It will give you can see a pier cap. You have to define the length of the pier cap. You have to know that the pier column, the height of the column. What I've done here is I've also included the piles to be part of it, so that to become easier to model. I would have actually stopped here, then I do this one later. But with time, you will know why I did that. For now, then the spacing, it is 5 meters. You indicate. If it is a pier wall, you don't put the spacing there; it remains 0. So you just get your normal pier wall. And then the material section, the material property, you also ask here. That is the first layout area where you are supposed to do in your model. The second part of the wizard is the section. Now this is where you define the different. This is why I was telling you that. Do you understand the bridge configuration? Do you understand the end? Because can you draw it? Because basically that's what you do. So you see the deck thickness, you need to know. So from your drawing, you need to know the deck thickness, the deck detail. This is the material properties are for the deck. The girder, this is now the steel composite girder, and the bracing. We talked about cross frames and diaphragm. That is the bracing here. Can either be, I can show you here. You see here, can be a bracing type, can be a single beam. So either a normal beam diaphragm or collections of angles giving you frames. So you can see your frames are here, and then so you specify all that here, and then you know where it's supposed to be. So you need the materials here. Then the number of girders, I have 6. I told you 4. In practice, most British literature indicates that 4 girders are adequate, but depending on the width of the deck. So here now you can see the spacing of the girders are actually 1 to 2 meters. So you see now, so these are like 6 of them. You have to specify. Then you also need to know the divisions of these girders. You know the cross frames. How many divisions do you have within a span? If this is 30 meters, how many do we have? So if I can show the division, you see here, this is 1, 2, 3, 4, 5. This is a 5 division per span. That's what is being called the division. So that is what you have, and it has gone back, so I have to open it here. Yeah, so the second one is the section. You define all this section. Composite, if you don't define this composite, it will not appear. So these girders are here. There are 6 girders, so make sure you define all of them. You define all these girders here. Very, very important. Then the third area you are supposed to work on is the load. This is now where you have to understand your decks. If you don't have any median here, you remove that. This is here, you call it 0. Median is you untick it, uncheck it, so it becomes 0. Then now you need to know what is here and here, the deck width, subtract it. The measurement is also being done from this, the left to right. So you have to know all this, specify it. Then your self weight, wet concrete, they are all here given here. The thickness, formwork. If you are going to use formwork, you have to indicate here. Barrier. You can either crash barriers have higher loads, could be about 8 meters if it's concrete. So there you put the exact here, but this one is for steel post. They are cheap, they are lighter. Wiring surface could be asphalt, but sometimes they can change to concrete. So conservatively, I have indicated 24, but could have been actually 22. Yeah, 22. That's the weight per cubic meter of asphalt. So you have utility. We also assume utility can be there. You indicate your utility. Then later on, then after here under load, make sure you define your load. You define this way. You define the moving load cases, either using Ashetor, either using Canadian, British standard, Eurocode, Australia, South Africa. All that you specify here. So it is very important. But now I think here we use Eurocode. So here is our Eurocode. You define, it's going to remove analysis. So let me remove it. So use Eurocode, and then here you define your traffic lane. So you first specify this lane. You measure from this area. That's something you must understand the drawing. You must know the measurement is from the edge. Where is the center line of the first lane, center line the second lane, the center of the third lane. You specify. Then later on, you can now include your walkways, and then you include your any other remaining lane that you are going to work on. So that is what needs to be done here. Then define the vehicle. It's a very interesting area, is vehicle defining. So here, this is how where you define your vehicle. You have to have a fatigue. I told you fatigue has to be here because it's still composite. And then fatigue, and then the CR connector is going to be affected more. So you have to have this road, bridge, footway, and fatigue. These 3 has to be all included. They are all here. So the load models are all given. So if I do road bridge, you see here, this is the load model 1. I can actually specify. I can now click on this and modify. You see what has already been entered. If you go to your Eurocode 2, you will see all these factors are there, where now they put the loading. You will find them there. Make sure this is what exactly you replicate here. Then for load model 2, you also look at it is a LM2. That is the 400 kilonewton axle load. It is only one axle load, only one axle with 2 wheels. And then load model 3 is the one which has the LM1 and LM3. So you have to have, I've chosen SV100. They are quite a different special vehicle. I use that one. I also use Eurocode, UK, national annex is what we adopt, or we use normally. So this is how you do in the wizard. That's where you do. That's the third, the loading area. Specify, and you make sure don't only fill this area and do it. No, you go, you check this one. the live load, then you define your moving load case, define the traffic lane, and define the vehicle before you leave the load case. So the load case, there are 4 things to fill. One is the way this body first. The second one are the vehicle. Then after you have done, you go to construction. In most cases, this is really by default. If you want to improve this number of days, you can do the duration in line with what you are working on. Then you can also define your reinforcement already here. You can define reinforcement here, or you do this. You can do it later when you are doing the design. This analysis stage you may not need it, but at the design you do. You come in here. This is the guide. This guide, if you say it is by 0.5, that is the line where you're going to put reinforcements in that direction, in the direction of the bridge. So it is input B method. Then the different reinforcement are here. Normally 12 or 16, we do it as a distribution. The main goes in that direction. Then you can either do how many a day, if you can calculate. If this is 2 meters and the spacing is 0.2, I know it's 11 bars, so I would put my 11 bars here. And then maybe I say this is 16. Then I say H bars will be defined, and my part 2, I click here, and then I respect that, and then I enter and I apply, and that's how we do the second one. Then also the third one. That's how we do your reinforcement. So having done all this now, then you say okay. Once you say okay, that's when you get this one here. That is as simple as that, the use of the wizard. Once this one is done, then we move to definition of the different loading. Then you come and define this lane. You saw there were 3 lanes. We defined lane 1, lane 2, and 3, but this remaining lane we did it now later, and the walkways you must define it. So when you are defined that's now when you are able now to go and run your analysis. So let's go back now to this. So this is in the modeling. This is layout model. So I've even given interface between the model, layout, guiding steps. So you have seen it there. Then figure 8 is interface between the model section. Okay. Interface between the model section, guiding steps. So this is a section. I talked about the different sections. To you. This is what we are calling the model section stuff here. This is the section. Model section interface, model load interface, and the model construction interface, and the layout interface. That's exactly what we have here. So this will not confuse you. So this is for the load interface. I told you in the load you are going to see this live load, defined lane, all that there. You do, I did not do it here, but you do all when you reach this model. You have 4 steps to undertake here. 1, 2, 3, and then the 4th one. Then we have the construction stage of Sonio. It is already there. So I think this would be easy. So some loading will be done as you are doing construction staging, and then others you do later on. Like I didn't include temperature, wind, water currents, and earthquake, because I just wanted for us to get used to this Midas and understand a few things. So in the loading, you set the load cases, dead load, live load, etc. Include moving load analysis and construction stage analysis. You already seen it there in the wizard. If you are not using wizard, definitely you will have to do it from first principle. Then you define actions, combination for design and checking. That one comes in now later. Then comprehend different loads and load path to ensure proper load distribution. Now, how you apply your load is very important. For wind load, you are going to do them on the side. Water current, you also do it on the side of the pier. When it comes to the temperature, you also know where you have to apply. We normally use the deck system. We don't go to the support system, because support system is believed to be in the water for some time, and so it is the most affected part of the bridge is the deck system. Yeah, so basically that is that on the loads, and this is now the static load definition. You can define the different loads. This is the lane. I wanted just to show you the different lane, but if you go to lane, if you come to lane here and you want to view your lane, you can highlight it all, shift, and just display. They are all here. And then the lanes are all given. If you don't want, you undisplay. That's what I was trying to demonstrate here. And then the next one now is the loading. The loading, I also indicated the traffic load. They're already here. I've shown you this one here, 0.61, 2.2. Please, these are all from the manual. If you go to Eurocode 2, the Eurocode loading, all those factors, and they call it those distribution factors and the rest, they are all given. Please read. Don't say that you did not understand some of the things. These are all in that's what I'm saying. It is important. If you have a specialized training in bridges, some of this literature we get them from the notes, even some before even you go to the manual. You already, the lecturer has already given you from the notes, and you're able to model. But you can look at those references and make sure you have them right. These are the different load. The load model 3, just trying to demonstrate, and I've already given you where you find this load, the loading. You need to, for the loading, it is important that you get it here. Dynamic traffic, I think this thing has covered where to give you, but let me show you from here. So you have your model and moving load cases are all here. You define them here. Then we have interface between the model and moving load case data. But when you are done with modeling, if you are done with modeling, there are these 3 things here. Let me increase there. You have the moving load. So from the moving load, you are able to see all these interface, and then from there you have load model 1, load model 2, all the way down. When you are done, you come, Eurocode comes, and then the traffic lane is here. In most cases, if it is not a slab, if it is not a plate, for plate you use this one, traffic surface. If it is the line beam, we use traffic line lanes. Now you define traffic. Once you are done with moving load cases, always go to analysis command and activate, and make sure you open the moving load case data. This is the one. You go to analysis, you come here to moving load, then you come all this, make sure the influence line dependent point is ticked, the box of number or line element also ticked. You can maintain 3 as a default. Then all that, normally we leave them as default. Even here, analysis results will be normal plus concurrent force or stress. So it has to be that. So all these boxes should be well done, checked properly. That is an analysis. If you don't do it, it will not run. So you have to make sure once you are done with all these moving load cases 1, 2, 3, 4. The 5th is when you go to analysis command, and then make sure you check that all this data, the boxes are ticks according. There's a box for track train load control option. We have influence generating point, analysis results. We have the plate, we have frame, then we have calculation filters, we have reactions, displacement. All that will be what will be done. So that is very important. And then this is now the normal loading. This is guardrail. I just showed you one example of the loads. Now this guardrail came from the wizard. When you did from the wizard, definitely it's already picked automatically. Then you have wearing surface. It also picked automatically. There's something which I left out that can be done. You can now do it. Is the raised walkway. Raised walkways is not captured automatically. You have to define it and then unload it later when you are doing your other loading, like the temperature and then the traffic and the rest. Make sure you do it. That one is a static one, not difficult. Static loading, you just apply that. You can decide to make it as a per linear meter and do it for all the girders, or you follow the pattern of wearing course, because this wearing surface has a pattern of load applications. They're all applied transversely, so you can still define the limits of raised walkways. Then you apply them per dummy slab. You know that these dummy slabs are spaced at about 1.52, 1.524 something. You, depending on what you have specified, you can apply. So you make sure it is linear transversely, but to the extent of the raised walkway on either side. That's how you apply it, and they are static in nature. Yeah, so that is it. So this is a demonstration of a traffic load interface. This is for load model 3. Yeah, that you can do for all if you want. If you are writing a report where there's going to do a lot of quality assurance, you can indicate all your loadings. You have no problem. Now for analysis, once you have done with all the loadings, you have done modeling, you have done the loading, all the boundary conditions are in place, then now you go and run analysis. Conduct various analyses such as static, dynamic, and backholing analysis. Assess the structure's performance under different loading conditions. You understand the bridge element and their behavior under various loads to evaluate performance. Okay, so the good thing, the software will design all these members, and if they are not passing, it will tell you, and then you do iteration. The most important thing with this software, they are iterative in nature. You understand your structure component, you understand the materials component, you should be able to do that. Excuse me. Yes, Lawrence. You already up? No, not yet. I'm coming. That is HD. And I think let me see if the formulation guy is around. I can with them. I think so. Let me check if they are in. Okay, very good. Thank you. Okay, thank you. Yeah, so basically for analysis, the whole process is here. All you need is just, and I think it is here, perform analysis. Once you are done, if it refuses, make sure you go back to check your boundary conditions, check the loading, and these other things. Make sure you check to see where the error is or the errors are before. So once everything is fixed, then it should be able to run. So once you do analysis, these are the things you can now see the output. You see the reactions. I pick for load case model combination. So this is now your piling system here. These are pile system. These are the reaction tip and reactions from applied load. These are for abutment, and then you come to moment forces, bending moment diagram. This is actually a BMD, yeah, bending moment diagram. You can see the moments on the piles, the collar beam, the what. You can see it clearly. So this is the moment. The red is the hogging moment because it's continuous, and then the blue is for bending. So all these moments you can now generate them. You can also generate tabulated moment, and you're able to have it tabulated, send it to Excel, and work on it properly. This is now for the pier support system. This is the end of the pier, which is connected by collar beam, as you have seen the other side. So this is how it is. The bending is. It's not showing much here because the girders, the way it is, the edge girders are directly on this pier support. Otherwise, if it was slightly off, you would see a cantilevering moment here properly. So we have that. Then we have now, this is the response from our piles. You can see it's behaving, but this is the egg in both directions. If it was in a single direction, it also appear, but it's showing both Y and X. This is Y and Z, yeah, Y and this MY here, MYZ here. So the middle one seems not to be, the external one seems to be affected more. Okay, so this is a shear force diagram, and then and this is the axial load from pile system, from pier support all the way down. So that is what you have. Those are the output of analysis. Now, so modeling our abutment using solid with the finite element analysis approach. Key areas to watch are bearing, flinch effects, abutment, base, connection, stress. So this steel composite, why I moved to the abutment system is to see the reactions from the deck system, how it impact, and I wanted to see because normally we keep asking reinforcement detailing, why do they detail here, why do they detail there? So it was very important to see physical from the solid, the stress distribution, the pressure bulb, so that you get to know. So here modeling is the same, is the coordinate based, loading also is nodal based, element drawing and connections, what you need to do, and then you do extruding commands to generate members. So this is done using that. You just make sure you do your nodal properly, generate the mesh, and then then you extrude to define the members. So this is the abutment, solid. Then this is how it is done. Then you have your dome abutment, the foundation, and then the wing walls. So that is what we have. These are the two different views. It's done by using solid. And then the loadings are here. These are the reaction from, these are reaction from here. These are reactions. Cannot see the reaction. Yeah, so this the reaction values I get from here. That's okay, fine. Which I think I could easily. Something I want to share with you here quickly. This here. So this is the reaction I picked. So I looked at the different reaction. I think I use even lower. I'm using 1, 2, and I can see even up to 1,400. Okay, fine. Demonstration, no problem. So now this is the reaction you apply on the node. These are the exact location, but you can still modify and refine it further to make sure you have the pedestal defined here. So in the next demonstration, we can do it. So then this is you apply the soil pressure at the surface, on the surface of these members, and then this is the vertical pressure, and then these are the outputs, the analysis output you can see from the solid stresses. These are the solids, the deformation. You can actually see that when you have a bridge abutment, the most affected element of the bridge abutment is actually the wing wall. So when the wing wall is not done well, it will separate from the member. That is for sure. And it start from up, not from down. You can see the failure mode very, very well, the deformation. So these are some of the things that the solid can actually tend to give you a better view. So now you can see under the bearing plinch. You see the deformation. That is why you always see that you have to have what they call bearing mat, the additional reinforcement layer that you do below or beneath the bearing pedestal to take care of these extra stresses that are generated. So use of only the abutment rebar to close the top doesn't work very well. This is for self weight, and then this is these are now the stresses under the bearing. There are 6 of them. You can see what's happening, the reaction effect. So this is I think these are soil. This is now how soil affect. You can see the pattern of failure that need to be. So you can actually get to know when you are trying to check the design or detailing. You need to know which area you need to concentrate. You see, we talk of punching. You can see the effect here. It has some implication here. So the whole thing tends, as it is being pushed, it tends to, the pressure bulb tends to come down here. You have the wing wall here. You can see the pattern, and then you can look at the stress distribution. You are able to know mostly that. If you do plate, you don't get to know the deeper implication of some of these. This is the plan of abutment foundation. So where the wing wall ends, you can see again down there how it is affected. So these are some of the foundation plan solid stress distribution. So use of solids tend to give you also very good and elaborate stress distribution that we need to follow. So I decided my most interesting area was here. This is very important. The bearing we talk about, how reactions can affect, and this is very important. And I think I wish I would be able to see the abutment solids, and then I can open one or two things, and then so this is how the whole thing is done. Modeling is very simple. You have to know, you have to use you can see the properties, the thickness, the boundary condition, the loading, the domain, and then the automation. You are meshing it up. Make sure this meshing inner domain is what now you do. Once you get the first phase, you can now mesh it up. Then from there you do the extrusion. Once you extrude, then you know, make sure you define exactly where you expect your load to be, the kind of element and other things that you need to. So from here, if you review solid stresses, I think this covered. I can't see this thing covered, so I cannot demonstrate that. So we just leave it at this. So this is what we can see here, and then the next thing is when you have the stress distribution, you can see that, and then the last one, I think that is what I can share with you briefly. I think this is our third time of discussing the pressure valve effect. There was an arch bridge concrete sprandle where we look at the effect of the arch on the foundation, where the pressure valve was tending to go past the certain, so it required the engineer to re-engineer the reinforcement detail to counter the effect of stress distribution. And then I think this is the second one, and we also looked at the anchor block. We also look at the effect using solid to see at the anchor block for post-tensioning girders. You realize that you cannot only use the reinforcement given, you need an extra reinforcement detail, the equilibrium, the spalling, and the popping or the busting. So definitely use of solids tend to open the mind of the detailer and the engineer to make sure those critical areas are attended to. So I think that is that. We shall look at the design later. This is on the analysis output we have discussed, though I've gone ahead and given some reference text to read. These are some of the reference texts that you need to read. Steel concrete composite bridges, sustainable design guide by Cetra. Then there is this one by David Collins. Then you have by Sanacha Arya. You have design of steel structures by Professor S.R. Satish Kumar and Santha Kumar. Then you have by Peter Knowles. Then there's BS 540 part 3 and part 5. Part 3 is basically the steel girders, while part 5 will give you some hint on the composite action, use of composite. Then you have fatigue design of steel and composite bridges by Mohammed Al Imrani. This one will help you to see the behavior of the shear stats and the rest of it. But there are quite a lot of literature on steel composite bridges. Even Steel Composite Wizard by Midas Tutorial will help you with the guide on how to model that. Then Composite Structure of Steel and Concrete by R.P. Johnson, Professor of Civil Engineering, University of Warwick. Please, there are quite a number of literature you need to read. Read as widely as possible, so that you are able to follow some of the things we are doing. So I think with that, I say thank you for listening. We shall continue sharing. If you have any data, any input, you will guide. That is my side of story, and it is as sketchy as it is. You can elaborate more with more in-depth reading. And this is not lecturing. I'm not a lecturer. I must emphasize that. I'm just a practitioner who is trying to share what I have with you guys. Thank you so much. Have a good day.